He's still in Tyson right now. I don't know, it's up to you. We can.
No, I think we should start because the other person is also coming.
He's coming?
Yeah,
Okay.
he's also coming, so maybe we should start.
Okay. So, we'll start. I probably won't take that long, but still, it's better if we start, I think. So, thank you very much for having me here. I'm Pinar from Ankara University, Turkey, and I'm doing actually biomaterials and tissue engineering work. Today, I hope I won't bore you with, basics of biomaterials. And for this boring presentation, I'm not going to start with this boring slide. The good news is I'm not starting with this, but just to let you know, is biomaterials has this much of a long definition from FDA point of view. But what's important for us is to define when does a material become a biomaterial. So what is a biomaterial? To define it and to define where we'll be using it. So anything in contact with human body is biomaterial for us. Let's say this apple or a pearl or the nacre from the sea, are they biomaterials? Or if we make them to behave within the human body to make something, make a therapeutic use, if it's then becoming a biomaterial. Let's say, are these metals biomaterial, or this urinate, or what is a biomaterial? So it's important to define what's the difference between this metal in contact with our ear or this metal in contact with our teeth, because one is biomaterial and one is not. So what makes this difference? So to define exactly what a biomaterial is, a biomaterial is a substance that has been engineered to interact with biological systems for a medical purpose. So this is very important for our definition, either for a therapeutic or diagnostic use, to treat, augment, replace, repair tissues or functions of our body. So as you all know and as you all use every day, biomaterials are used for a variety of purposes within our bodies. And you're familiar with most of these, as I know. So functions of biomaterials, we have four major bullets here. Biomaterials either do load bearing or load transmission activity, or they control the fluid flow in order to stimulate normal physiological conditions, as in the stents over there. They either do passive or active space filling for cosmetic or functional reasons, or they sometimes, like in the case of pacemakers, generate some electrical stimuli or transmission of light or sound. They do one of these functions. So biomaterials science is a multidisciplinary field. The research that we do has been stimulated and guided by advances in so many fields. One of the most important things is the feedback we get from you guys, because otherwise we don't know what to design. So we need the feedback from you to what you need in the clinic so that we can design systems towards that. So I'd like to just talk a little bit about the history of biomaterials, how this whole thing came into life. It started more than 3,000 years ago, and we see from the history that Egyptians and all the other old people used all this kind of biomaterials in their practices with no knowledge of sterilization or toxicology, inflammation, this kind of things, but they used it. So by the start of aseptic surgery and all these advances in the medical field in the beginning of 19th century, the biomaterials started to become as a scientific area. And the synthetic plastics, with the use of the synthetic plastics in surgery, biomaterials field advanced. And the first applications of biomaterials started from when an ophthalmologist actually realized that the pieces of plain shreds were in the eyes of the pilots, and they were not causing any adverse reactions in the eye. So that they realized that maybe, and this was PMMA pieces, so they thought that, well, maybe we can go ahead and use this plastics in the body so that we can help people do better regeneration. And then in the 1960s, polyethylene and stainless steel started to use in hip prostheses and everything. So the important thing for us is Biomaterials as a field evolved starting from bioinert materials, and then they go all the way to bioactive and functional tissue regeneration pathways. So maybe we can go a little bit and say what are these things. So bioinert materials, as we understand that bioinert, once placed in the human body, has minimal interaction with the surrounding tissue. Generally a fibrous capsule is formed around the implant, and it sometimes is a good thing and sometimes is a bad thing, because in most of the cases this fibrous capsule prevents the implant integration with the surrounding tissue, and which is something that we don't want. So bioactive materials, when we implant them in bone, let's say when they get in touch with surrounding body fluids, there is an ion exchange reaction which causes the formation of a biologically active carbonate layer on the implants, and this layer is chemically and crystallographically, which means by ions equivalent to the mineral phase in bone, so that good bone implant contact can happen. So there are examples of that. So biodegradable materials, which we as tissue engineers really like using, which we take advantage a lot, is this biodegradable materials, or bioresorbable is another way of saying that. They are, upon placement within the body, start to dissolve and slowly and replaced by the advancing tissue. So we are taking advantage of this and making scaffolds with that. I'll give you some examples. So tissue reaction of biomaterials, we can say toxic, obviously, which is not what something that we don't want. So inert, bioactive, and biodegradable materials. As I said, tissue reaction, tissue forms a non-adherent capsule around the implant. Examples are this. And bioactive materials, we want tissue bonding to the implant, like in the case of titanium alloys. Or biodegradable material, tissue replaces the implant in polylactides, glycolides, and there are advantages and disadvantages of using this, as you all know. So I just wanted to put this picture here to say that regulation and approval process is a pain, and somewhere that no one wants to go too much inside, because it's a long journey. Ghazi showed you the plate, right? The thing that we patented and trying to get it produced. It's been more than 6 years, I think. It's so long a journey, even though you're using the material that's been used for, I don't know, maybe in the last 50 years, you still, because in every individual case, if you want to produce something and to get it used in the human body, you have to go through a lot of pain, because FDA never approves a material, or maintains a list of approved materials. But each and every time when you want your product to be approved, they go through all of this stuff, because for the specific case they are looking for the specific this and this and that. So everything goes through a lot of this processes. So everything you see downstairs, over there, is a lot of work, really. So to get this regulation is so much, and FDA regulates different products, different types of things, and it costs a lot of money. I won't go obviously into numbers, but it costs a lot of money. So to start manufacturing a device, we start choosing the material, and then the tests and the physical properties and this and that, and screen the candidate materials, and then the chemical and physical and biological characterization has to be done. So from a bench to bedside, from the laboratory to the clinic in your hands, there's a long path, and starting from the idea to the patient, there's this stages of identification of the problem, design, synthesis, testing, all of these things. And today I'll just want to talk about how do we do this selection of materials. So where to use which type of material obviously depends on the anatomical location and the required outcome. If you want it to dissolve away, if you want it to stay, if you want a permanent fixation, or if you want it to, I don't know, there's this anatomical cues, as you all know better than me, and as I said, potential need for removal. But how to choose which type of material to use, there are important parameters, and surface, mechanical and thermal properties of materials are important for us when we want to design something starting from scratch. And today, since thermal properties are out of scope of this talk, I'll be just talking about surface and mechanical properties and just try to give you the basics of what are these, and maybe you have, when you want to design your own system one day, you'll have an idea to where to start. So if we want to talk about surface properties, we should obviously first define what a surface is. A surface is an interface between the boundary region between two adjacent bulk phases. For example, a gas solid or vapor liquid, liquid solid. This three has a surface between their interfaces. So you may think of surface as a 2D plane, but it's actually not. It's a 3D plane, a 3D environment, because in the molecular scale there are lots of things happening within the surface. So the important thing to know is whenever you implant something to the human body, the first reaction the body gives to the implant is mediated by the implant surface. So whatever the bulk property is, it doesn't really matter. The surface is very important, and systems move toward lowering their free energy. This is the law of thermodynamics, the first law of thermodynamics. So surfaces do this to lower their free energy by geometric changes or bonding, like proteins on it, or dynamic rearrangement. So the design of the surface is very important for the success of your implant within the body. So surface energy and contact angle are two important properties for us. Within that surface there are chemical bonds, as you can imagine, and these bonds are when they are unsatisfied at the surface, this is the measure of the surface energy. When there are more unbound bonds on the surface, there is more surface energy, and the contact angle is a property that we measure to see how energetic a surface is, how hydrophilic, how hydrophobic a surface is. This is, as Professor Dieter said in the morning, just Newton's law of total force is equal to zero. This is the same application of the same thing here. When we put a drop of liquid on the surface, it forms sometimes a thing like that. As you know, it can be worse or better. And the angle here and the sum of the forces here gives us the surface energy. The important thing for you to know here is some surfaces have more energy and some is high, and we want low surface energy so that it won't cause any reactions in our bodies. So surface roughness is another important thing for us to consider, because almost all interactions between cells, tissues, and the metal implants, generally ore implants, occur at the surface, as I said. And this kind of impurities on the surface is something that we don't want, because it can cause leachables, and so that it can cause adverse reactions within the tissues. In terms of mechanical properties, again, Professor Dieter gave very comprehensive information about mechanical properties. But the thing is, for the biomaterials point of view, tensile and shear properties are important, bending and time-dependent properties. So this will be maybe a small repeat of what he said, but these are important things to consider. So types of forces that can be applied to a material are this, as shown here: tension, compression, shear or torsion. Engineering stress and engineering strain, or stress-strain curves, are important for us also, as he said. So stress is the force divided by the area, and strain is the percentage of how the material deforms for us. So there's this Hooke's law here. Young's modulus is this E that also we saw this morning. This is the same curve, the stress-strain graph. To here, yield point, so this is a repeat of what we've gone through already, but just to repeat, this is the elastic deformation here, and this is the plastic deformation here, and the toughness. So With materials with strong bonds like diamond or cobalt chromium alloys, the modulus of elasticity, this E here, this Young's modulus is high, so that the given stress produces only a small amount of strain. So the material won't deform how much stress you apply on it. It means for materials with weaker bonds, like polymers or golds, the moduli is lower, so that with the application of lower amount of stress, you will have higher strain. So this depends on the selection of the material depends on what type of application you need. And toughness is also another thing that we pay attention to, because it's the ability of a material to absorb energy and physically deform without fracturing. And this is the area under the curve gives us the toughness of the material. So hard brittle materials have a small toughness value, as you can see here, and it depends on the material property. So if we look at the material here, the strength of this material gives the ability of the material to resist to an applied force without failure. So it depends on how much force you apply on it so that this can withstand that force is the strength. And ductility is the ability of a material to be stretched or shaped without breakage. And how ductile a material is sometimes is important, as you said, to pre-shape it before surgery or whatever. So this strength and ductility are important properties to consider. And strong implants are used for large bone defects or major fractures, and ductile implants, as I was saying, when contouring is necessary, for example, you need ductile materials to use. So when we see different types of biomaterials like ceramics, metals, or polymers, how they behave in the stress-strain curves, small toughness is ceramic, so that when you apply a small amount of stress, it will resist it and then it will break the ceramics. So that what makes them brittle is this. And large toughness is metal, so they can withstand a lot of stress, but they change shape most of the times. And polymers can go very high strengths, and they can strain, so they can withstand this. So if we go into the basics of the stress-strain curve again, this material one, as I said, are very characteristic to ceramic materials. Stress proportional to strain, as I said, is the elastic deformation. When you unload the material, you can the material still unload the force. The material still remains the same thing. And fracture after a point is just applying, so that it won't, the ceramics won't change the shape, but they you can apply the force, and after some point they break. And in the metals, stress proportional to strain after up to a certain point, and then they can deform, which gives us the plastic deformation. So stress increases very slowly, and with increased strain followed by fracture is happening in metals. And so if we compare in between the metals and how they behave in Young's modulus gives us the stiffness, you can say NiTs are lower, and tantalums or stainless steel or cobalt chromium alloys are higher in stiffness, so that they can carry more load. So polymers, there is a wide range of things you can obtain with polymers depending on their molecular weights and depending on their properties. So elastic and plastic deformation can be obtained with polymers depending on their chemistry and properties, as I was saying. So stress proportional to strain in, let's say, material 3, this curve we are looking, you can obtain this kind of behavior with polymers. You can also obtain this one. So it, as I said, depends on the molecular structure of the polymers. So when you have this kind of a material, let's say it doesn't fracture at a very high strain value, so this means that you can stretch the polymer as much as you want. So there are some specific cases which is needed. And in plastic deformation, we mean, let's say up to this point, when you apply tensile strength, tensile force to this metal piece, let's say, it goes back to its original shape, but after this point, it starts to dissolve. If we see in the molecular level what's happening, the chains of the polymers or the crystal structure within the metal is deteriorating so that it changes its shape, and further stress increases, deteriorates the shape, and it doesn't go back to its original shape. And Professor Dieter also talked about this time-dependent property creep, which means that plastic deformation of samples under constant load over time. So think of having a fork in your hand and you started bending it. You cannot bend it the first time, but if you do it 1 million times, after some time you will observe that there will be a crack and it goes away. So this is what happening in also orthopedic implants. So this is creep. It happens in phases, and this is an important property for our implant designs or material choices for implant designs. Let's take a ligament and elongation versus time at a constant load. So if you take a ligament and apply a load on it, it will suddenly elongate, and then it will elongate for a considerable time, even though the load is constant, so it will keep elongating. Or if we take the other thing, if you take a ligament and do the tensile testing, and then you keep that load, you will realize that there is a loss in the load, drop in the load at constant extension. This is called stress relaxation. I guess these two things are important in also our design for biomaterials. So another time-dependent property of mechanical things for us is fatigue. In fatigue, the structures fail as a result of cyclic stress, as I said, that may be much less than the optimal tensile strength. So it cracks. We can see a metal piece here which the initiation starts here, and after you go lots of times of cyclic stretch of tensile loading on this material, it cracks. So a number of cycles and stress applied to that, you can see this fatigue is a very important cause of failure. So the success of a biomaterial is related to several factors, as I said, including material related properties, general condition of the patient, surgical technique, and proper follow-up. Obviously, for our point of view, biomaterial, considering material-related properties, should retain its physical properties, should be non-toxic or carcinogenic and anti-allergic, have long service time, easily sterilized, be biocompatible, and bulk properties are chemical composition, surface properties, mechanical properties, as I said, and long-term structural integrity. And we should take into account all of these things to start to design our systems. And biocompatibility is a very major issue to consider for our case. It's defined as the ability of a material to perform with an appropriate host response in a specific application, because whenever we put a material within the human body, we want it to be biocompatible, otherwise obviously it won't work. Examples of biocompatible surgical materials are stainless steel, titanium alloys, as you all know. And the more biocompatible a metal, the less negative tissue reaction occurs. Gold is one of the most important ones, but obviously it's cannot be used as bulk properties. So there should be a performance, application, synthesis properties, and all these things should be in a good coordination for us to have a successful implant. So how does it work? When we implant a material, is the implant surface properties, as I said before, is the main issue that controls the biocompatibility of the material in the first place. Because when we see the surface properties, it can be rough or smooth, and it affects the attachment of cells on the surface. And the cell is generally, the cells, when we implant the material, is strongly attached to rough surfaces and loosely attached to smooth surfaces. So depending on what type of application you want, for example, if you want a good contact with bone and implants within a bone, bone plate, let's say, if you want a good contact, and if you don't want to remove it, you will better have rough surfaces so that it will have better contact. But if you want to remove your implant after some time, it's better to have smooth surfaces so that it will have less interactions with the surrounding tissue. So the following occurs, as I said, first proteins are attached, covered on the surface, and then the rest of the things gives us the success of the implant. So if it's not biocompatible, inflammation occurs, possible consequence of chronic inflammation, and in this case, for example, this metal oxide passivation layer is ruined in this point, and it can give us ions reached to the body, which can cause carcinogenic or other things. So if we look into a little bit of types of biomaterials, there are three types of materials, the three major classes, which are polymers, metals, and ceramics for us. There are advantages and disadvantages of using all of them. Elastic modulus is one of the most important ones. So when we want the material to carry high load, we generally want to use this kind of strong materials, and conductivity, density, ductility, other kind of properties are also important things to consider. I won't go into detail obviously of this, how the cubic structure and how metals are densely packed. That gives the strength of the metal. But the important thing to know here is in the atomic layer organization of metals, there are free electrons, which these electrons can move all throughout these structures, this cubic structure, so that it gives the conductivity and the properties of the metals. When processed suitably, they contribute high stress, as I said, because of their cubic, highly packed, dense structure. Even within these metals, there is a great degree of heterogeneity within the material properties. Cobalt-based alloys, let's say, have higher Young's modulus, and titanium have less. So depending on what kind of application you're going into, you will have different properties. And typical shape of a metal stress strain curve, as I said, is again like this elastic and plastic deformation. Since we talked too much about that also in the morning, I won't go into details. So metallic biomaterials are used almost excessively for load-bearing applications and also for blood-contacting materials, because they have really good blood interactions. They don't disturb the cells of blood generally, so they generally don't cause thrombus, so they are used in that. If we see the strength of pure metals versus alloys, which one to choose? You obviously see in your also clinical practice that we generally alloys are preferred, because they are most of the cases stronger. Because when you look at pure metals and their atomic structures, there are dislocations within their grain boundaries. But when you have an alloy, this atomic structure is stabilized with this alloy material. So packing of two different sizes of metal elements generally prevent physical dislocation of the lattice structure. That's why alloys are generally more stable and generally more preferred. And also within the nature, we see, let's say, titanium generally also is in combination with aluminum, is used mostly in our cases. And in nature also, metals are found in combination with oxygen most of the time. So metals and metal alloys are commonly used and they are preferred. So as I said, they are used in blood contacting devices and hard tissue repair. Corrosion is a very important issue that generally diminishes the success of the metal implant, because you have to remove it if the corrosion happens. Implants with rough surfaces, as I said, is especially susceptible, and ions released from the implant can start so the passivation layer on the metals are very important, and when it's broken, when it's damaged, this corrosion is more possible to start. So we have to pay very good attention on the passivation layer, and while producing and while applying it, we have to keep the passivation layer on the metals. If we look at ceramics, it's coming from the Greek word meaning the art and science of making and using solid articles formed by action of heat and earthy raw materials. This is the meaning of the thing. So as you all know, we are using ceramics as biomaterials for composed of metallic and non-metallic elements, and dental and in your applications. They are highly used because they can carry high amount of load. So advantages is inert, high wear resistance, high modulus, the stiffness is high, so it's important in load-bearing applications. The disadvantage is brittle and low tensile strength and for fatigue resistance. So this aluminum oxides, bioactive glasses, and calcium phosphates are being used as ceramics. And if we look at their, as I said, they are brittle, they have low toughness, so they can carry load, but they are susceptible to breakage if we load more than it's needed. So generally used in bone and dental related applications because the structure of the ceramics are very close to bone and dental tissues. That's also why they are used. So polymers, polymer is also coming, a word is coming from the Greek, many units. It means so there are many monomeric units coming together to form the polymer. And polymer molecule is a chain, for you to know, it can go from very small to very, very large. And examples are polyethylene that you all use, and other things. And DNA also is a polymer. So what's important for us to know how big these chains are, because it defines their mechanical properties. Polymer architecture also affects the properties. They can be linear in ring structure, comb structure, star. This stuff, how the 3D architecture of the polymer is being designed, affects the mechanical properties. So you can do a variety of things with polymers. So this all design structures affects the mechanical properties. One interesting thing I thought you would be interested in is the number of atoms. Generally, carbon is the backbone in polymer chains in biopolymers. So if the number of carbon atoms is 1 to 5, let's say it's a gas. If it's up to 15, it's low viscosity liquid. If it's up to 25, it's a very viscous liquid. And if it's so the only thing that changes here, it's all ethylene, starting from the ethylene to ultra high molecular weight polyethylene that you're using in your clinical applications. It's the same thing, ethylene, but what's changing is the molecular weight of the polymer, how you start to add on top of it. So polyethylene is inert and it non-degradable, good material, good biocompatibility to use. So polymers, as I said, are huge. I'm giving a lecture of 14 weeks on the use of polymers in orthopedic surgery. So there's a lot to consider, but it's just for you to know that there's a wide variety of things that you can do with polymers. They are versatile, used for different applications. You can do as soft as a thing to go into to sit in your eye as a contact lens, or you can do something as hard as this, or to put in your body to carry load. So there's lots of things. From now on, I just want to give a little information on tissue engineering and what we are doing and how we are using these biomaterials to try to engineer tissues within our bodies. So current clinical practice is you're using biological or synthetic grafts, but the big question mark here is how functional are these grafts that we are using, that you are using. So tissue engineering comes into play in these cases. Using the biomaterials and using the advances in stem cell research, now tissue engineers are able to produce tissues that can be implanted in real patients to save lives. And these alive tissues that we produce in the lab are saving lives. So tissue engineering holds promise for lots of applications, including orthopedics. And this Macy that you're using maybe is an example of tissue engineering. Let's say it started from the very beginning because you use stem cells or patient's own cells and a scaffold to hold it, and it's an example. So tissue engineering market is growing heavily, exponentially, and the green bar is here, orthopedics. So there is lots of research is going on, lots of money is being paid on orthopedic applications. So how is it happening? We have three major components: scaffolds, cells, and bioactive agents. And in this trachea technique that I showed you before, what people have done is to produce this scaffold that mimics the patient's trachea and put cells on it, and then implant it, after growing it, implant it back. The important thing here is the scaffold, as I said, the architecture of the scaffold, because as if you're building a building, let's say, you first put the scaffold outside, and then after the building is done, you remove the scaffold and the building stays there. It's the same logic here. We produce scaffolds for the tissue to grow in, and after the tissue grows, we are producing the scaffolds from biodegradable materials so that this materials degrade within the body, and we are left with the natural tissue. So this is the thing I showed before, the biodegradable polymers come into play here. We are producing the scaffolds for this. And there are some specific cases where the scaffold design needs to be anatomical shaped. There are also applications in orthopedic surgery, but I'll give you the example of this face construction here, where this poor lady has a gunshot in the middle of her face and lost most of the, as you can see here, the maxilla. So the eye is dropping, the nose is going. There is cosmetic as well as functional problems here. So the routine plastic surgery, the reconstructive surgical application, what they do is to take a piece of costa or fibula, they were saying, and try to design it in a way that they can reconstruct the face. So this is the best case scenario that was happening in Hopkins when we were there. So this is how they are routinely trying to treat this patients. But obviously you can see that this is not the best case because you cannot put the face back. Also, this is an example from the skull injury where, again, a piece of bone were put here to try to protect the brain from damage. But what tissue engineering and what advances in 3D printing gives us today is that we take the images from the patient and we design anatomical shaped scaffolds that should fit perfectly into these defects, and we go on and print these with biodegradable polymers so that we can put the patient's face back. And also, this is an example from a skull problem where we can produce this anatomical shaped piece to go into that thing. So I'll just want to give a little bit of what is 3D printing. It is a computer-aided design and manufacturing process where we take the medical file and produce our 3D structures by computer-controlled environment. It's a layer-by-layer technology, so we start from the very top bottom layer and we go all the way up to produce whatever we want. In this case of a mandibular condyle, let's say we started from the medical image and produced this 3D printed scaffold. So there is this famous example of a neuron. So this is just to show that this is doable with chondrocytes and scaffolds that is made from a human ear. So These are science fiction, but there are also science fact applications also in the orthopedic surgery. So I won't go into details, but the important thing is fused deposition modeling is the approach that we are using to print polymers. And this is just examples of how we 3D printed scaffolds, and we can grow cells in them, just to show you that we can put growth factor releasing systems on these scaffolds so that they can be functional. And then we can apply this 3D printed scaffolds into rabbit or rice models. We have completed all of these, and hopefully this 3D printed bone pieces will be commercialized soon, hopefully, so that we can obtain better bone regeneration with these scaffolds. So 3D bioprinting, as a last comment, holds great promise for the future applications also in orthopedic surgery, and we are hoping that we can help you in designing functional constructs that you need, so that you can have easier time in the OR, hopefully. This is all I'm going to say. Thank you very much. I just didn't want to go into detail of nothing but just superficial something. I hope it was helpful. If you want to discuss anything.
Thank you very much. I didn't know that she is doing like that, such great works. That was, I'm very surprised. Yes.